Structure and operation of MOS transistor MOSFET. The basic structure of an N-channel MOSFET is shown in figure. This four-terminal device consists of a P-type substrate in which two N+ diffusion regions, the drain and the source are formed. The surface of the substrate region between the drain and the source is covered with a thin oxide layer. The metal or polysilicon gate is deposited on the top of this gate dielectric. The mid section of the device can easily be recognized as the basic MOS structure which was examined in the previous sessions. The two N+ regions will be current conducting terminals of this device. Note that the device structure is completely symmetrical with respect to the drain and source regions. The different roles of these two regions will be defined only in conjunction with the applied terminal voltages and the direction of the current flow. Here you can see in this figure the physical structure of an N-channel enhancement type MOSFET. A conducting channel will eventually be formed through applied gate voltage in the section of the device between the drain and the source. Diffusion regions. The distance between the drain and source diffusion regions is the channel length L, and the lateral extent of the channel perpendicular to the length dimension is the channel width W. Both the channel length and the channel width are important parameters which can be used to control some of the electrical properties of the MOSFET. The thickness of the oxide layer covering the channel region TOX is also an important parameter. A MOS transistor has no conducting channel region at zero gate bias is called an enhancement type or enhancement mode MOSFET. If a conducting channel already exists at zero gate bias, on the other hand, the device is called a depletion type or depletion mode MOSFET. In a MOSFET with P-type substrate and with N+ source and drain regions, the channel region to be formed on the surface is N-type. Thus, a device with P-type substrate is called an N-channel MOSFET. In a MOSFET with N-type substrate with P+ source and drain regions, on the other hand, the channel is P-type and the device is called a P-channel MOSFET. The abbreviations used for the device terminals are G for the gate, D for the drain, S for the source, and B for the substrate or body. In an N-channel MOSFET, the source is defined as the N+ region, which has lower potential than the other N+ region, the drain. By conversion, all terminal voltages of the device are defined with respect to the source potential. Thus, the gate to source voltage is defined by VGS. The drain to source voltage is denoted by VDS, and the substrate to source voltage is denoted by VBS. The circuit symbols for both N-channel N channel and P channel enhancement type MOSFETs are shown in figure, while the 4-terminal symbolic representation shows all external terminals of the device. The simple 3-terminal representation will also be used extensively. Note that in the simple MOSFET circuit symbol, the small arrow always marks the source terminal. Consider first the N-channel enhancement type MOSFET shown in figure. The simple operation principle of this device is control the current conduction between the source and the drain using the electric field generated by the gate voltage as a variable, control variable. Since the current flow in the channel is also controlled by the here you can see the figure circuit symbols for N channel and P channel enhancement type MOSFET. Formation of depletion region in an N channel enhancement type MOSFET. Drain to source voltage and by the substrate voltage, the current can be considered a function of these external terminal voltages. We will examine in detail the functional relationships between the channel current, also called drain current, and the terminal voltages in order to start current flow between the source and the drain regions. However, we have to form a conducting channel first. The simplest bias condition that can be applied to the N-channel enhancement type MOSFET is shown in figure. The source, the drain and substrate terminals are all connected to ground. A positive gate to source voltage VGS is then applied to the gate in order to create a conducting channel underneath the gate. With this bias arrangement, the channel region between the source and the drain diffusions behaves exactly the same as for the simple MOS structure we explained in this session. For small gate voltage levels, the majority carriers holes are repelled back into the substrate and the surface of the P-type substrate is depleted. Since the surface is devoid of any mobile carriers, current conduction and the source and the drain is not possible. Now assume that the gate to source voltage is further increased as soon as the surface potential in the channel regions reaches -5 FP. Surface inversion will be established and a conducting N-type channel will form between the source and the drain diffusion regions. Figure. The channel now provides an electrical connection. Here you can see in this figure band diagram of MOS structure underneath the gate at surface inversion. Notice the band bending by more to 5F at the surface. Formation of an inversion layer channel at an N-channel enhancement type MOSFET. Between 2 and plus regions, it allows current flow as long as there is a potential difference between the source and the drain terminal voltages. The bias conditions for the onset of surface inversion and for the creation of the conducting channel are therefore very significant for MOSFET operation. The value of the gate to source voltage VGS needed to cause surface inversion to create the conduction channel is called threshold voltage VTO. At any gate to source voltage smaller than VTO is not sufficient to establish an inversion layer. Thus, the MOSFET can conduct no current between its source and drain terminals unless VGS greater than VTO. For gate to source voltages larger than the threshold voltage, on the other hand, a larger number of minority carriers electrons are attracted to the surface, which ultimately contribute to the channel current. conduction. Also note that increasing gate to source voltage above beyond the threshold voltage will not affect the surface potential and the depletion region depth. Both quantities will remain approximately constant and equal to their values attained at the onset of surface inversion.